Okay, this is lesson 3.3 on rules of differentiation. So in the previous lesson, we learned that slope is now called derivatives. And so we're trying to find a faster way of finding the derivative of your functions, right? In the beginning, we use limits to find the derivative, but it is a very, very long process. So now we have some tools under our belt, and we have some ideas here to help you with some quicker way of finding the derivative of each of polynomial function first, and then later we'll actually find it for trig functions and exponential functions and so on and so forth. Okay, so power rule for integer function. This is actually our bread and butter for a while, right? So this is the power rule. What this is saying is when you take the derivative of a polynomial function, the power drops down to the front to multiply with the term, and then the power subtracts 1. So if you're taking a derivative of x cubed, it becomes 3x squared because you drop the 3 down and you subtract 1 from the exponent, okay? All right, you can also take out a constant. If you can factor out a constant, you can pull it out and then just take the derivative of the function itself and then multiply it back with a constant. That's actually super helpful too. You can add derivatives, you can subtract derivatives, and then product rule says, hey, what if you have two things multiplied together? Right now, we are only focusing on polynomial functions, but this is super helpful when we have other types of function. So we're introducing this concept first using polynomial function because you can actually check your answer, all right? So what this is saying is you have two terms. You have a u times a v. So you're going to take the derivative of the first, so that's u prime, multiply the original form of the v, plus, now keep the original form of the first one and take the derivative of the second one. So that will be your derivative. Some books actually use this notation, u prime v plus uv prime. So that's another way to do it. I'm not a huge fan of memorizing it this way because if you have three terms, then students get really confused. But if you have three terms or more terms than two multiplying together, basically it's like w times x times y times z. You go with the first. So you go w prime and everybody else stays the same, x, y, z. And then w stays the same now. This is the second one, x prime, y, z. And then the next one, wx, and then y prime, z. And then the last one, wxy, and times z prime. So you take the derivative of one of the terms each time. You don't take it all at once, and you multiply it by the rest of the ones that didn't get taken the derivative of, okay? Next is a quotient rule. I like this one a lot. Again, some people memorize it differently, so I'm going to give you a few of the things that I've seen over the years. So you have a top function divided by the bottom function. So the formula is v u prime minus u v prime all over v squared. So it does matter which one is first because you are subtracting. So you actually start with the bottom function first and then multiply by the derivative of the top minus the top function times the derivative of the bottom and then bottom squared. Another way I've heard people say this, they say low d high. So the low is the bottom. So low d high, the derivative of the top, minus high d low all over low squared. So that's another way to memorize this. Okay, let's see this in action. So the first one says you are looking for the derivative of g of t equals 6 times t to the 5/3, right? So you're going to take the first and second derivative. You're going to take the derivative 2 times, basically. I'm asking you to take the derivative 2 times, all right? So g prime of t is equal to 6. Now drop down your fraction, t. And don't forget, you got to get really good at subtracting fractions now. You got to subtract 1 from this fraction. So you get 2/3. So you clean this up, you get 10 t to the 2/3. Beautiful. Now, you take the derivative one more time, so it's g double prime, right? So it's 10 times 2/3, t now 2/3 minus 1 will give you a negative 1/3. So be in a good habit of rewriting it into a fraction. So it will be 20 over 3, t to the positive 1/3. You can leave it as t to the 1/3. You don't really have to rewrite it as a cube root, but writing it in this fraction form is going to be super helpful for later chapters, okay? All right, so this is a rational exponent, and you see when you take the derivative, it just keeps creating more and more fractions. Now, number 2, we have a true polynomial function. So I'm going to take the derivative. In fact, this one I'm going to take the derivative until we get to 0. So let's see how many times it takes, how many iterations. I'm going to do the derivative backwards. Backwards to this problem. I'm going to do it in standard form, highest power first. So negative 5s to the 4th now becomes negative 20s to the 3rd because you drop down the 4 and you subtract 1 from the exponent. And then 4s squared, so positive 4s squared now becomes 8s. Minus s, there's a coefficient, so minus 1, And then 15, what is derivative of a constant? It's 0. Think about it as a constant. When a function is a constant, y equals a constant, a number, it is a flat line. What is the slope of that? It's 0. So anytime you have a constant, the slope is 0. So the constant is gone. Okay? All right, let's keep going. Let's take another derivative. So if I take another derivative, I get negative 60 s squared plus 8. Okay? You notice how this is a true polynomial function. You actually lose terms as you go. You get smaller and smaller and smaller. So it's pretty awesome. F triple prime will give us negative 120s. The 8 is gone. Keep going. Oh, at this point, you just put a little 4 here. That's the fourth derivative. That gives you negative 120. And then at the fifth derivative, because now you are taking a derivative of a constant, you get 0. So it takes 5 derivatives for you to hit 0. And you know that because your highest power is 4. Oops, sorry. Your highest power is 4 here. And so you always need one more number than that power to finish out your derivative and get all the way down to 0. Okay? All right. When you encounter a problem like number 3, it is best to rewrite the equation into a polynomial function. So rewrite your exponents as a fraction, right? So if you rewrite this, you get f of x equals 3x squared plus x to the 4/3. Now you can take derivative. F prime of x equals 6x plus 4/3 x to the 1/3, right? You gotta get comfortable with rewriting your exponents and see that once you rewrite your exponent, it's much easier to take the power rule of the terms, okay? Take one more derivative. We're practicing taking derivatives, so take one more derivative. You get 6 plus 4/9 x to negative 2/3. And again, I would have urged you to rewrite these all into one fraction because that is a very good habit to have for later chapters, right? But more importantly for f double prime here, because we have that negative 2/3. So if you rewrite it as 6 plus 4 over 9x to 2/3, okay, you write this as a one single fraction, you get 54x to 2/3 plus 4 all over 9x to 2/3, right? Again, it doesn't look like I'm simplifying this, I agree, but this is very helpful when we are actually applying this to the applications of derivatives, okay? All right, now we have the product. We have a product here in number 4. Because it's a polynomial function, you actually don't have to apply the product rule. You can actually go ahead and multiply this out, like distribute this whole thing out and then take the derivative. But again, I want to show you that it does work. So we're trying to use the product rule to show you that the product rule of polynomial function to show that this actually does work very nicely. All right, so you have g prime of x. Okay, you take the derivative of the first one, which is 3x squared times 2x squared plus 3. And then you take the derivative of the second one, but keep the first one. So x cubed minus 7 times the derivative of the second one, which is 4x. All right, clean this up by distributing. You get 6x to the 4th plus 9x squared plus 4x to the 4th minus 28x. So you will get 10x to the 4th plus 9x squared minus 28x to be your final answer for this g prime. Now, if you were to do this the second way, which is multiplying it out, you would have changed your g of x equals, I'm going to distribute this out. I get 2x to the 5th plus 3x cubed minus 14x squared minus 21. Then I take the derivative, so g prime of x is 10x to the 4th plus 9x squared minus 28x. See how I get the exact same answer? So it's really depending on what your comfort level is. And again, this is only useful because we can do this because we have polynomial function. If we have anything added to this, then we have to use product rule, okay? So for something like number 5 here, I would strongly recommend that you just rewrite the equation first because you only have a single term in the front. So if you distribute the x to 1/2, you get 3x. All right, so we have 1/2, you have 2. So 2.5 makes it 5 halves. Minus 2x to the 1 times the 1/2 on the outside, so 3 halves. Plus 5x to the 1/2. So again, you have to get comfortable in terms of knowing how to combine your fractions and rewriting it as an improper fraction. Okay, so go ahead and multiply this out. Drop your powers to use power rule here. You get 15 over 2x to the 3 halves minus 3x to the 1/2 plus 5 over 2x to the negative 1/2, right? So again, normally I would ask you to go ahead and actually multiply this out and rewrite it as one fraction. Right, but again, there's a lot of terms here. And I really would like you to practice the next layer of the derivative. All right, so this is the first derivative. Second derivative, you get 45 over 4x to the 1/2 minus 3 over 2x to the negative 1/2 minus 5 over 4x to the negative 3/2. Again, this is just really reminding you to have practiced how to subtract the fractions and get your exponents in the right order. Okay. All right, I am going to go ahead and use product rule with the next one again. So k prime of x equals, taking the derivative first, that gives me 4x minus 4. Keep the second one, 6x minus 5 plus 2x squared minus 4x plus 1 times 6. Okay. All right, go ahead and multiply this out. You get 24x squared minus 20x minus 24x plus 20 plus 12x squared minus 24x plus 6. Okay, that would give me 36x squared, so that's these two. And then negative 20, negative 24, negative 24, so 2, 4, 6. So minus 68x, and then plus 26. Okay? All right, so that will give me the first derivative, and then I would like you to go ahead and take the second derivative of this. So k double prime of x gives me 72x minus 68. This is a polynomial function, so if you were being prompted to do so, you can actually keep taking a derivative until you hit 0. Okay? All right, so that's really good product rule. Now, what if I have fractions? Then you got to use quotient rule, right? So quotient rule says f prime of x. By the way, this is the high and this is the low, right? So because high is the function in the numerator and low is the function in the denominator. So we get low d high, oops, d high is 4, minus high d low all over low squared. All right, please don't do voodoo math. A lot of people will really want to do this, and it happens every year. They will want to do that. You cannot do that. You cannot cross those two out because that term is not shared in the second one up top. All right, so go ahead and distribute and see, clean up what you get. You get 12x plus 8 minus 12x plus 15 all over 3x plus 2 squared. That would give you 23 over 3x plus 2 squared. Now, I'm not going to ask you to find the second derivative of this particular fraction of this particular function because you have something squared in the denominator and you don't have enough tools to find that derivative. So we're going to leave it as is. All right, so take the first derivative only. All right, keep practicing. We're going to practice this one, f of t. All right, so you have low d high minus high d low all over low squared. All right, so again, it's the algebra that really trips a lot of students up. So make sure you check your work, make sure you're distributing, and you watch your negatives, all right? So 8t squared minus 16t plus 24 minus, you distribute, get 16t squared. This gives you 30t minus 16, so plus 14t, and minus 30, all over t squared minus 2t plus 3 squared. That gives me negative 8t squared minus 30t, 24 plus 30, so plus 54, all over t squared minus 2t plus 3 squared. It's pretty rare that you get to factor the top and clean up the some of the terms up top and bottom, but you know, it doesn't hurt to check. This one actually doesn't factor out really nicely, so we're going to leave it like this. Okay. All right, next one, I will still rewrite the top function as t to the 2/3. That way it's a little bit easier to deal with. Now, if it were the other way around, if it were a single term on the bottom, I would actually ask you to go ahead and divide it through and kind of distribute that so that it becomes one polynomial function again and you don't have to use quotient rule. Honestly, I avoid quotient rule as much as possible because I find that with the subtraction, it gets a little bit more confusing. So I try not to do that. And there are other tools later that will help us kind of overcome that hurdle of not using the quotient rule. Okay. All right. So I have quotient rule here. I have g prime of t is low d high. So 2/3 t to the negative 1/3 minus high d low all over low squared. Okay, I clean this up. We're going to distribute. You have t here and negative 1/3 here. So if when you combine those, you get 2t to the 2/3 minus 10 over 3t to the negative 1/3 minus 3t to the 2/3, 3t minus 5 squared. That will give me negative 10 over 3t to the negative 1/3 minus t to the 2/3 all over 3t minus 5 squared. Let me do a quick check here. Yeah, so again, if you could, you really should try to clean this up. You will clean up and get negative 10 over 3t to the 1/3 minus t to the 2/3 all over 3t minus 5 squared. To get the top into one fraction, you multiply the right-hand side here by 3t to the 1/3 over 3t to the 1/3. That way you can combine them, and it actually works out really nicely because then it becomes one whole t. This is actually very prone to happen here. So you have negative 10 minus 3t all over 3t to the 1/3, and this 3t minus 5 squared is also in the denominator because it was in the denominator in the first place. It still is in the denominator. Okay, so that would be a more cleaner version of that derivative. Okay, what if my function has fractions like this? What do I do? So first thing you want to do is rewrite this as 1 plus x to the negative 1 power, and x to the negative 2 power, and x to the negative 3 power. Anytime you can rewrite it as a power, a polynomial function, you should, because then it becomes much easier to tackle when you're taking a derivative. Okay, so p prime of x equals, well, the 1 is gone, so drop down to negative 1, so negative x to negative 2 minus 2x to negative 3 minus 3x to negative 4. Now, of course, if you were being asked to do more with this particular derivative, you would rewrite it as negative 1 over x squared minus 2 over x cubed minus 3 over x to the 4th. I'm just going to ask you to take another derivative. So you go back to this line right here, and you get 2x to the negative 3 plus 6x to the negative 4 plus 12x to the negative 5. So again, rewriting this, 2 over x cubed plus 6 over x to the 4th plus 12 over x to the 5th, right? So what I'm trying to show you is that when it's not a true polynomial function, it is going to go do something like this where it just keeps going, where it keeps increasing or changing in the exponent. It's really not going to go away like a true polynomial function. Okay, what do I do here? What if I have 5x to minus 4 squared? Well, then treat it like 5x minus 4 times 5x minus 4. And that way you can use product rule, right? So h prime of x equals derivative first is 5 times the second one, 5x minus 4. Okay, and then plus, now I keep the first one, 5x minus 4 times 5. And that would give me 10x minus 20 plus 10, oh, sorry, not 10x, 25x, sorry. So my mind is not here. So 25x minus 20 plus 25x minus 20. That would give you 50x minus 40 for this derivative. So you would do the exact same thing for the next one because you're now cubing this function. So if you treat it like 2w plus 1, 2w plus 1, 2w plus 1, right? Now, when you take the derivative, s prime of w, you take the derivative first, so that's 2, times 2w plus 1, there's 2 of them, so squared, right? Now, same thing. I'm going to take the root of that. That's 2. And then this is the same. This is the same. This keeps its original form. So 2w plus 1 squared. And then last but not least, the last one is also 2. And then another 2w plus 1 squared. So really, there's 3 of these. So there's 6 2w plus 1 squared. And you could keep it like this. You don't actually have to distribute it out because it's actually much easier to take the derivative if you were asked to take it again. Okay? All right, so those are all the rules we have for differentiation. Hopefully that will make it much easier, much quicker for you to take the derivative of functions. Okay, that's it.